So now we've looked at graphs, what we need to look at is the way that they're connected and the way that we traverse a graph. So many applications of graphs involve getting from one vertex to another. For example, finding the shortest route. We looked before how they can represent how cities are interlinked together. We looked at that it could be distance, it could be time. If this is a network, how do we get from one router to another and the quickest route? So that could be one application of a graph. Another application could be finding a path, so finding a way out of a maze. And these paths are formed by travelling along the edges from one vertex to another. So if there's a path between vertices, then we can find out what that is, otherwise we can disconnect and find a different route. So we have standard algorithms for doing this. And here's an example of a graph on the left hand side. And this is a representation of this maze. So the A is the start, and you've got J there as the finish point. But how do we get the shortest path, and how do we actually find the route from A to J? So we have to visit every edge and vertex in a systematic way to find that. So to escape the maze, the graph traversal algorithm must avoid getting trapped in that maze. So the maze must be traversed in such a way that we've visited every vertex, every aspect of that, and we've found our way. So the algorithm must mark every vertex when it's first visited, so that we know we visited it. So we start at A, we visited A, what exists from A, and there's B and there's D. So knowing that these exist from B to D, once we've visited A, we know this is here, and then we can traverse to B. So we keep a track of where we've completely explored and where we've just visited. So we're going to rely on Boolean flags, and we've got 3 Boolean flags: undiscovered, discovered, and processed. Undiscovered means that that vertex has not yet been found. Now, as a programmer, we know that exists, but as an algorithm that's tracing through looking for this, then we don't know that exists. Discovered means that we found it, but we've not yet been down every edge. So we've discovered that B exists, but we haven't travelled any further. We've discovered E exists, but we don't know what's beyond E yet. We've got processed. Processed means completely explored. So once we've done everything possible, so looking at this graph, imagine if we've gone all the way to C, there's nowhere else to visit. We've explored it, we've found it, we've visited it, it's been processed, and then we are backtracking to these other algorithms, to these other vertices. So that's the process, undiscovered to discovered to processed. So with a breadth first search, this is one of our key algorithms for doing that. And if we look at this with an undirected graph, then first of all we need to assign a direction to each edge. And we're looking to go from the discoverer, which is known as U, to discovered, which is V. So in the standard algorithm you'll see the terms U and V. Now this gets quite confusing if you read the algorithm out, because you're going from U to V, and U is the parent of V. So each node has exactly one parent, except the roots. If we look at these, every single, I'm calling them nodes now, they can be interchangeably called nodes and vertices. Every node, every vertex has exactly one parent. There's one route it's come from. In the maze, if you're now there, there's one route you've come from to get there. You've made a decision to turn left, turn right. So here is our tree, our graph again. Another name for this could be a tree. Because it's got what we call a root, it's got a key starting point. The only thing that makes this not a tree is we've got directions on these arrows, and that's something we'll look at a little bit later. So because it's directed, we're still going to refer to it as a graph. Now the process of a breadth first search is that we start at node A And we're going to explore all the neighbours of A. So we're going to go down each edge. So we're going to explore, and we found D. D exists. But I don't want to get too heavily involved with that yet, so I'm going to come back to A. Now B exists. We're going to come back to A. So I know that D and B exist. Now I'm going to explore all the unvisited neighbours of the neighbours of A. So the neighbours of A is D and B. The unvisited neighbours of the neighbours of A is E and C. Then I'm going to visit the neighbours of the neighbours of A. And that becomes F and G. And then visit H and I and J. So eventually you're visiting the neighbours of A and the neighbours of the neighbours of A, the neighbours of the neighbours of the neighbours of A, the neighbours of the neighbours of the neighbours of the neighbours of A, and so on. And it is breadth first. And that's where it gets its name from. So a typical exam question, maybe you're given a graph like this, and you're asked to output the order in which the vertices will be explored. A, D, B, E, C, F, H, H, I, J. It would always do it left to right unless the algorithm advised otherwise. But looking at this without a pseudocode algorithm in place, we're working down left to right down that tree graph. So it defines the shortest path from the root to every other vertex in the tree. And this is really, really useful for finding the shortest path problems. So once a vertex is discovered, it's placed in a queue. Since the vertices are processed in, first out, the oldest vertices will be expanded first, and they're the ones closest to the root. So I'm going to give you a little look at the algorithm, and the actual tracing of this won't feature in this video, but it gives you a chance to try to understand how this works. So what we would first have to do in algorithmic terms is have an array that includes state and parent of the vertices that we've got. And all the states, as we mentioned before, the state will be undiscovered, then it'll be discovered and processed. So at the start of the process, every vertex is undiscovered, and every vertex has no parents, because we don't know what they are yet. And the starting state, the root, in this case A, have discovered a nil. We've got this process, we're going to NQ. So we're going to NQ in the queue the starting state. So we're going to take the queue and queue it in the queue. And there is the algorithm. So that algorithm, while not queue empty, do U, dequeue the queue, Q, process the vertex U. For each V adjacent to U, do process the edge U, V. It sounds like a bit of a rhyme. That's the algorithm. And this is where this video will end, just giving you that little introduction of what the algorithm looks like. What I would like you to do is to take those two algorithms using the previous tree and try to produce a trace table that covers this. Now you'll have to draw a queue to store the contents of the queue. When we process an edge, you can basically just tick that off. But I'd like you to just spend a little bit of time looking at that breadth first algorithm to see if you can start to make a little bit of sense before this is covered in the lesson. We're going to spend the lesson tracing this and looking at examples, but having a little bit of time beforehand should help that process. Okay? Thank you very much for listening.